In problems 25 and 29, we're supposed to find the exact value of the logarithm without using a calculator. And for problem number 25, we should always know that log base anything of 1 is always going to be 0. And that's because if you set it equal to, if you set the log equal to x and solve for x, you would solve for x by taking 2 and raising it to the x power is equal to 1. Well, 2 to the x equals 1 can be rewritten as 2 to the 0, and x then it would equal 0. So therefore, the value of this logarithm excuse me, is 0. Over here, we're going to do the same thing. We're going to use that technique of setting the log equal to x, solving for x. We rewrite the logarithmic equation in exponential form, so we have 1/2 to the x is equal to 16. Remembering from the last section that in solving an exponential equation, we can recognize that both the left and the right side can be expressed as a power of 2. So we would get 2 to the negative 1 to the x, so that's 2 to the negative x equals 2 to the 4th power. And then you get negative x, therefore negative x equals 4, so x would have to be equal to negative 4. So then we say, therefore, the log base 1/2 of 16 is equal to negative 4. So negative 4 is the value of that logarithm. I was going to say logarithmic expression. And so that's it. Now, in 39 and 45, we're trying to figure out the domain of the function, and understanding how logarithms work, you're not ever allowed to take the log of 0, and you're not allowed to take the log of a negative number. So in order to set this up, we would have to look at the argument, and the argument in finding the domain of a function, if it's a log function, the argument has to always be non-negative. No, I take it back. The argument always has to be positive. It can never be 0 either. Sorry. So x squared greater than 0. Well, x would be all real numbers. X would be all real numbers except for 0. So you can write that using the inequality notation, or you can use the all real numbers interval notation, all real numbers to 0, but not including 0, and then all real numbers greater than 0. And so either one of those ways of writing the answer is fine. In number 45, again, we always set up an inequality. Anytime we're trying to figure out a domain of a log function, just take the argument and set it greater than 0. Don't, whatever you do for this, don't multiply through by x, because you're going to be changing the structure of the problem, because if x is a negative number, then you have to flip the inequality symbol. And when we were solving inequalities using rational expressions, never did you see me multiply both sides by an x like that, the denominator, to make the denominator go away. The only time you can multiply both sides of an inequality by something is if you know that something is never going to be negative. And we don't know that here. But what we do know is, if you remember rational inequalities, we would set the numerator equal to 0. We'd get x equals negative 1, and the denominator equals 0. Those are the two key values that we would put on our sign chart. So we have negative 1 and 0. And as x moves from negative infinity to positive infinity, so does the value of the sign of the fraction x plus 1 over x. So we just want to make sure we pick only x values that would make this a true statement. Therefore, those would be the acceptable real numbers to replace x with in the logarithmic equation, logarithmic function. So if we pick a value to the left of negative 1, let's say negative 10. Negative 10 plus 1 is negative, and negative 10 is negative. So we have a negative divided by a negative. That's a positive. In between negative 1 and 0, let's pick negative 1/2. Negative 1/2 plus 1 is positive. Negative 1/2 is negative, so we have a positive divided by a negative. Therefore, the fraction's value would be negative on that interval. And then to the right of 0, both the numerator and denominator would be positive, so therefore the fraction would be positive. So the domain is all real numbers to the left of negative 1, not including negative 1, because that would make an argument of 0. And then all the real numbers to the right of 0, and again, not including 0, because 0 would make the denominator 0 anyway. And so that right there would be these would be the intervals which would represent the domain of the original function that we see listed here. And that's it.